So many of you that have been following the news have probably heard that the Kepler team announced yesterday that they had something like 1,200 new exoplanets around something like 1,000 suns, not black hole suns, just normal suns. And there's some really crazy systems where they have one that has basically 6 planets that are transiting in front of the parent star, and there's another one that has 5. So that's pretty amazing. I think before this, there was only a few systems that had 2 transits of the planets around them. So this is like the time of exoplanets, and it's a pretty exciting time. They also have something like 50 or 60 candidate rocky Earths that are in the habitable zone, but of course they won't know for sure that they're orbiting at about 1 AU, like our Earth, until they have confirmation of a couple other passes, right? So they've seen the first pass, and in some cases maybe they've seen 2 passes in the first years of data. They're just going to want to see it again to make sure it's not something else. But it's starting to look really good that there are lots of Earths around stars that are like our own. Yes?
They were also looking for rocky planets around red dwarfs, too, though, that would be much closer to 1 AU?
Well, so it depends exactly on the configuration and what the period is, of course, right? There's a relationship between period and semi-major axis.
So is that 50 or 60 around sun-like stars?
Yeah, around F and G stars, yeah. Okay. All right, so problem set number 3 is on B-Space, I believe. It's been posted. That'll be due next week, as you know, Wednesday at 11 a.m. For this week, if you haven't already, please finish reading chapter 17. For next week, we're kind of going to bounce around throughout the book, kind of touching on all the different subjects of black holes and accretion disks and accretion luminosity. And this is the last sort of stuff that you'll be tested on in your first midterm, which is in 2 Tuesdays from now. 18.2, 24.4, and then there's this weird chapter which is stuck in towards the end of the book on AGN. It's not weird, it's just weird that it's where it's stuck. What I really want you to read up on is 28.2, which is just sort of understanding the emission processes. But 28.1 is a reasonably good survey of what it means when we talk about an active galactic nucleus, or quasars. You won't be tested on sort of the demographics of quasars, what's a radio quasar, what's a Seyfert 1, etc. But this will help you get some context for 28.2. So if you're running low on time, you can really just skim through that. I already mentioned the exam. The colloquium today at 4 p.m. in number 1 LeConte is by someone named Riekers, and he's at Caltech. He'll be talking about gas in the universe and how gas is used to both make stars and also fuel the sort of growth of galaxies. So yet again another talk by an extragalactic person, and he'll be talking both about optical and radio observations of those galaxies. In addition, there's a talk today that I thought you might also be of interest, which is about the statistics of planet discovery. So it's not so much about the astrophysics of planets, but more about how we actually infer when we look at some of these very noisy data streams, whether we actually have a planet or not. And this is given by Jim Berger from Duke University, and that's at 2 p.m. today in Evans 1011. That's all I had on logistics. Was there anything else? Anyone want to ask? Okay. So let's see. Last time we derived gravitational redshift in the weak field limit. Remember, invoking the principle of equivalence, setting up that rocket experiment, and coming up with this general form, which I just gave you, which works both in the weak and the strong field limit. And this shows that the frequency observed of some light, let's say, by an observer at infinity, is going to be equal to the frequency emitted times this factor here, 1 minus 2 gm over r0. This is r0 is where the light is actually emitted, c squared to the 1/2 power. This number is something approaching 1, so this whole thing here is going to be slightly less than 1, so the frequency is going to go down, which means that the wavelength is going to go up. This is gravitational redshift. Likewise, if you just invert this, between two different intervals as measured basically at some fixed radius from this point mass, m. So this is what we called this tau, or something called proper time. So if I basically look at my watch and I shoot a laser pulse every 1 second out towards somebody at a radius much farther away from where I am relative to the center of this mass, the person at infinity would measure something different, and in particular, they would measure a higher or lower rate. Lower, right? So, well, okay. So let's be clear about. Let's go through the equation here. So if we have this whole thing here, something close to 1, this whole thing is going to be slightly less than 1. We invert this, so indeed this is going to be higher, right? Time dilation. Okay. We then talked about geodesics, and we talked about masses freely floating in this curved space-time. And we said that the integral of minus ds squared over the path length that it winds up taking is either a maximum or minimum. And remember, ds squared and the integral of ds squared for photons is always going to wind up being 0. That helps us a lot when we start doing cosmology. And perhaps most important is that we introduce the Schwarzschild metric. I'll just do that. Metric. And this is just ds squared is 1 minus 2gm over r c squared to the, c squared dt squared minus this entire quantity dr squared 1 minus 2gm over r c squared plus r squared d phi squared plus r squared sine squared phi d theta squared. Remember, it actually made sense for us to posit this metric because we're basically just talking about this isolated point mass in spherical coordinates rather than doing it in dx squared, dy squared, dz squared. Of course, you could do that transformation if you really wanted to look at the metric that way. And of course, in the absence of mass, right, if I just strike off the m here and strike off the m here, we basically wind up getting what we had before when we talked about special relativity and the special relativistic space-time metric. And of course, we did that in Cartesian coordinates, but that's what it would wind up. If we just got rid of this term right here, that's what we would wind up seeing in spherical coordinates. So this is pretty useful because if we want to actually start making measurements in this space, and remember the way to really think about this, if you want, is that we have some sort of coordinate grid. And now I'm just sort of drawing this in 2 dimensions here. Here's our coordinate grid. Here's where our mass m lies. And I can localize myself at some radius r1, and then I can do experiments and pass information back and forth between some observer at r2, and we can measure each other's clocks progressing. Of course, the symmetry that we enjoyed in special relativity is completely broken, right? Because R2 knows that he or she is at a different radius from the distance here, from this massive body, because they feel a different gravitational potential. So there is a totally broken symmetry. If I shoot a laser beam down from R2 to R1, is that light redshifted or blue shifted? Blue shifted. It's falling into this potential well. And when we go back the other way, of course, it's redshifted. So there is this sort of reciprocity that we had. The reciprocal nature of special relativity is now completely broken. There are frames that are more special than others, right? Some that are closer to this massive body, right, are going to feel a stronger potential. When we localize ourselves in this metric, right, so here we would wind up moving around, and maybe the z-axis is coming out of this plane here. We would be at a d theta, we'd be at a theta of pi over 2, right, into this plane right here. We localize ourselves somewhere in this metric. And if we want to make measurements of distances, say, between R1 and R2, so here we would replace this differential d with a capital delta, we can see what our meter sticks would wind up measuring. The important thing here is that we like to think of ourselves in this space as being, say, 50 meters from this massive body, or 1,000 kilometers or whatever, right? The way to think about these little r's and these thetas and these phi's is that this is the location of where we live, or we're going to be making measurements in our own local inertial reference frame in this coordinate space. What we actually measure with meter sticks is going to wind up being different. In particular, we said that the proper length, d script L, is just going to be the square root of minus ds squared. And if I wind up integrating that, of course, I get the proper length from R1 to R2. But leaving it in differential form, this is just dr1 minus 2gm over rc squared. This is for a simultaneous measurement with delta t is equal to 0. And this, we said at the very end of class, is greater than dr. So this measurement that I wind up making with meter sticks, if I put myself in these coordinate distances, say of like 1 light year from this massive body, and here I'm 1.1 light years from this massive body, if I start walking and making measurements from R1 to R2, I actually make a measurement which is larger than 0.1 light years. So the way to think about this is that this coordinate system, as I've drawn it out, perhaps you think of these as sort of equal tick marks on the board. But indeed, the way what's actually happening, the way we think about it, is that these tick marks are actually stretched out. Okay. Any questions about that? Yes?
How do you have the square root of a negative of something squared?
I can do whatever I want. Well, it's really because that's how we define our metric. Sometimes you see the time-like term as the negative and the space-like term as the positive. If you're making measurements of distance, and again, we're just using the space-time metric to make that measurement, you typically do that measurement at the same time, right? If I'm measuring where the beginning and the end of my yardstick is, meter stick, if you like that stuff, you're going to wind up trying to say that at the same time. It'd be silly to say, where is the end now, and where is the end 3 days from now? Because if I'm moving, that would be a little bit weird. So you usually just lop this off. So there's actually already a negative sign here. So this negative winds up multiplying times this negative here. So it's actually a positive value.
So it's actually the quantity of negative,
Yes. It's negative of this quantity here. Now, it's perfectly appropriate if you made measurements of meter sticks both in time and space, where you're measuring the ends of both of these things. Remember, this is a space-time interval, right? So this is between two different events. We're totally entitled, if we want to do this at different times. In principle, you could wind up getting an imaginary value of this length. But the whole idea of making this measurement of proper length is to do it simultaneously in the same inertial reference system. This works also in special relativity, and we'll see it also works in an expanding space-time. Did that satisfy you enough?
It's just weird that d squared equals something
Um,
just mathematically.
yeah, I mean, other books will do it the other way around, right? This is really just a sign convention. But remember, we had to have, when we were doing our Lorentz transformations, and of course there's an equivalent transformation when we're talking about general relativity, we had to have this time term and the space term be of opposite sign, so that when we did the transformation, we wound up being invariant under that transformation, right? So no matter where I am relative to this mass, I'm going to wind up still measuring this same space-time interval, which is sort of freeing, right? I can do it in any frame I want. Yes?
So would ds become what?
Yeah, in general it is. Yeah. Yeah, that's right. Okay. Any questions about sort of stretching of space-time making measurements with rulers in this curved space-time. All right, let's see what sort of practical implications there are for all this. One obvious thing to think about is orbital motion. In a curved space-time. And just to make our lives easy, because it's more or less almost completely intractable if you don't do this, we're going to consider a circular orbit of a body with no mass, essentially, around a body that has mass, of a test particle around mass m. And we'll also posit that the period of the orbit is just going to be 2 pi divided by omega of the orbit. So this is the angular velocity. What are the units of this? Yep. Radians per second. Good. Thanks, Pauline. All right, so the general relativistic ingredients to sort of solving for this orbit is one, that we're going to start off with the Schwarzschild metric, of course. And two, because this test particle is just freely moving through this space-time, the path is going to be a geodesic. So remember, that's where we just said that we're going to wind up getting a maximum or minimum of this ds squared, or minus ds squared. All right, so let's do this in the proper coordinate space. So unlike this sort of spider web that I drew here, which is on the plane of the board, we're more or less going to draw that motion in this direction here. This is the z direction, how we oriented it before. And we'll wind up making this angle theta here is equal to pi divided by 2. So this motion of the particle is just going to be around in this circle here. The real question is, what is r? First of all, what's dr? Why? Because it's circular. Because it's circular, dr is equal to 0. What else isn't changing? Theta isn't changing. Good. Yeah, we're just going to keep ourselves in the plane. So d theta is also equal to 0. And phi is just going to sweep around 0 to 2 pi, 0 to 2 pi. Sine theta is equal to 1, so we can look at our Schwarzschild metric, and we can simplify that. We wind up getting that ds squared is equal to 1 minus 2 gm over rc squared, c squared dt squared, minus r squared d phi squared. Okay? So that's our intermediate result. That's our metric that we have to deal with, given these constraints where we already posited that the orbit was circular. Of course, you could relax that and make the orbit elliptical, but then you have to pay attention to the fact that you have an r changing and a phi, which is going to wind up changing. So the maximum, finding the maximum here, we can take the square root of both of these sides, and we're going to do an integral over ds from time t equals 0 to a time p orbit. So we're basically going to go around one circle, and we're going to more or less measure this length of ds. And this is just basically the square root of all that stuff there. c squared winds up multiplying out there. We're going to get the square root, the integral square root of c squared minus 2gm over r times dt squared minus r squared d phi squared. This is all inside of the square root. Again, limits of integration are going to be the same. Okay? Now the trick here, because we obviously have two different, we're trying to integrate with time, but we have this pesky phi here, is that there's of course a relationship between phi and time. So we want to do a transformation of d phi to dt. And there it's pretty clear that d phi is just 2 pi divided by the orbital period times d time. Units work out, of course, right? Because p is in units of time. This is a time in the numerator. And we also want to get this in units of angular distance. So this is a 2 pi. Right? We're just seeing how fast this is changing. And obviously, if I increase the period, then d phi is going to wind up changing more slowly. Right? It's going to be a lower number. If I decrease the period, then we're going to go around that circle much more quickly. Everyone agree with that? All right, so we can put that in. We wind up getting from over there ds, integral of ds from 0 to p. And now I'm dropping the subscript of orb. From 0 to p is the square root of c squared minus 2gm over r minus r squared 2 pi divided by p squared, all quantity dt. What's nice about this integral, this integrand right here, is that it doesn't depend on time. R is not changing with time because we posited the circular motion. The period's not changing with time, right? Because it's just going to keep on going around and it's unchanging. Again, because we have circular motion. And so this becomes a trivial integral. This is going to be p times some constant on the right-hand side. What does it mean to have a maximum or minimum of this quantity on the left-hand side, which is what we said was the definition of a geodesic? What's that? Yep, the derivative of 0. So I can basically take the derivative of both sides and set that equal to 0. Well, d by dr, right? I can take the derivative of it with respect to anything I want. So d by dr is equal to 0. I can just make my life easy, and it's clear that if I'm trying to minimize or maximize this right here, I can just basically square the whole thing. Doesn't really matter how I wind up doing it, but this is going to wind up equaling 2gm over r squared minus 2r 2 pi divided by p squared. I can square what I have before. So this is the 1/2 power times p. I can square 0. I still get 0. I can just put a p squared here. Doesn't matter, right? I'm going to get rid of this p squared. And now I'm going to wind up solving for p in terms of other quantities. And so I just wind up having this right here winds up equaling, I can put the negative over to this side right here, and I wind up getting that gm over r squared minus r 2 pi divided by p squared is equal to 0, which just gives me that p squared is equal to 4 pi squared gm times r cubed. Well, there's a 4 pi squared right here. Oh, okay. Let me explain to you again. Yeah, maybe I rushed through that. Sorry. Somebody said that the way I think Roy said this, right? If we wanted to figure out the maximum or minimum of this quantity on the left-hand side, which is what I said that we had to do. By the way, I said that the geodesic is where we maximize or minimize this quantity minus ds squared. You can show, of course, that if you're maximizing or minimizing a quantity, whatever that quantity is, if I take the square root of it or I take the square of it, at that location of all the other parameters, I've also reduced the maximum or minimum, right? Right. If this is my here's some terms that I care about, and here's my function. If I wind up taking the square of this, so f squared, it still happens at the same x location, right? And likewise, if I take the square root of it. So this is we're trying to do the geodesics over here, okay? I can take the derivative of this to help me find where that derivative is 0. It gives me an inflection point, gives me a maximum, or it gives me a minimum, of course, right? So I set this whole thing equal to 0. We said that everything that's happening inside of this integral, this is a trivial integral to write down because this doesn't depend upon time. So the answer of this integral is just p times this constant of all this stuff that's inside. I set that equal to 0. And so that stuff is this stuff. I can then square everything that I had just to get rid of all the square roots, because I can square whenever I want. And then I just solve. Sorry, that wasn't clear. Yeah, okay. It is beautiful. Messed up by a non-beautiful explanation. All right. Kepler's third law. Of course, the modified Kepler's third law has this m being the mass of the object and the mass of the central body itself, but we just posited, we're just talking about test particles, right? And of course, in a realistic system, the mass of that body and the mass of this tiny little planet or test particle are going to wind up moving around the center of mass of that system, and that will mean that the effective radius will wind up changing of this particle, because we're going to wind up having some little perturbation due to the fact that this thing actually has a little bit of mass. But forget all that stuff, because we're just trying to do this in the simplest possible terms. The important point of all this is, A, you've just seen how you actually use the space-time metric to figure out stuff. That's good, I think. And we'll, again, use this sort of trick where we say d by d something of this left-hand side is going to wind up giving us distances when we start talking about cosmology. But this is the first time we've seen this. The other really important thing, of course, is that we derived Kepler's third law without making any reference to what kind of particle it is we're talking about, right? This particle could have been a photon. Nowhere in this whole discussion did we talk about the mass of that particle, right? We didn't have to use F equals gmm over r squared to come up with Kepler's law, which is probably how you did it in high school physics. We get to do this just because the metric tells us this has to be the answer. Again, under the assumption that we have circular motion. Yes? This, when we take the integral of this and find the minimum, or actually find an inflection point, find a minimum or find a maximum of this quantity, that tells us how freely floating particles actually wind up moving. For the special case of photons, this actually has to equal 0. But yes, if we're not exerting any other force, a local force, in the reference frame of this moving particle, the only thing that's around is this mass, which is curving space-time, then this has to be true. This is what this is what a geodesic is. Any questions about that? Now, in a real system, of course, this Schwarzschild metric is inexact, right? Again, because we have multiple masses. Each one of those masses has their own space-time curvature around them. Even you have your own little aura around you of your little curvature. It's very infinitesimal, but you have this. You used to think of this, this gravitational attraction between you and everything else. Now think of this as you just carrying around your own curvature. No one's laughing. Okay, fine. Whatever. Okay. But so when you think about motion of objects inside of a solar system, when those objects have a mass which is not completely negligible, but even just a small fraction of the mass of the central body, you automatically have a very, very complicated metric, right? Because as this object is moving, it's dragging its curvature around it, which means that if I'm standing there and watching this object move by, I'm going to wind up seeing this curvature changing as the object comes by and then as it moves past me, right? Even if I'm just stationary in whatever metric I want to put myself in. Yes?
Is there a lag between the object moving and the person?
Yeah, I mean, there can't be, just like, this idea of information transfer can't go faster than the speed of light. The idea is that if I want up adding mass somehow, although you can't do that instantaneously, it has to come from energy somewhere else. But, if I just wind up having more mass than I did yesterday, then the curvature around me will change. And somebody that's very far away, like on another exoplanet in a different solar system, will not know that my mass has changed because that information basically is traveling at the speed of light. Now, we think that these changes of the curvature of space and time propagate outward at the speed of light, but we don't know that for sure, which is kind of an interesting prediction of general relativity. It's something that might actually get measured fairly soon. So think about it this way. You've got this sort of overall curvature from this central body, but then you wind up having other bodies moving around it, carrying their own sort of local spatial curvature. And as viewed by an observer far away, they're going to wind up seeing this rippling of space and time. And this rippling of space and time, this information is going to wind up getting carried away. It turns out that that information is also, when you're passing information, you're also passing energy. So information is actually slowly, and energy is slowly leaking out of the system. It turns out that idea is a great way to make measurements of some of the predictions of general relativity, the fact that there are these things called gravity waves. Gravity waves are nothing more than the propagation of the ripples in space-time, essentially moving away from a binary system or a set of bodies that are in mutual orbit. And you can imagine the amount of the ripples that you wind up getting wind up depending upon how massive those bodies actually are, how close they are, etc. There was a discovery in the 70s of a pulsar system. Does anyone remember what a pulsar is? Anyone tell me what a pulsar is? Yeah, it's a rotating neutron star. Why do we call it a pulsar? So there's some sort of arbitrary angle between this beam and the spin, and it's going to wind up sort of processing around, right? And if it comes into your line of view, there's also a relativistic effect, by the way. These particles are moving out relativistically. If it comes into your line of view, you wind up seeing a little blip. Usually it's a radio blip, so we have radial pulsars, although we also have gamma ray pulsars and X-ray pulsars. And then when it's not pointed towards you, you don't see it, and then it comes back. Neutron stars are very dense. They're spinning very fast in many cases. In this case, we had a 57 millisecond pulsar, so its period was 57 milliseconds for a body that's sort of 10 kilometers in radius and a mass comparable to that of the sun. And it was in a 7.75 hour orbital period around another neutron star. So here you have two point masses, one of which is acting as a great clock, because this thing is just spinning around super quickly, right? And we can just measure the pulses. And then they're moving in and out of each other's gravity. Pulses moving through of the pulsar, moving through the gravity of the other one, the curvature induced by the other one, going to wind up experiencing the same sorts of effects that you've already thought about it on your previous homework. In particular, you're going to wind up having deflection of light. And in particular, also, the light spends more time near that pulsar. So you get a bunch of different effects, which can be measured quite accurately. General relativity, remember, predicts that you wind up getting orbital precession. And this is something that was essentially a post-diction of the orbital precession of Mercury as it moved around the sun. Remember, that was something like 47 arc seconds a century. This thing is moving by arc seconds a second. I mean, it's precessing dramatically because of this incredibly strong gravity. The period of the orbit. So now I'm measuring this pulsar, and it's this great clock, right? I can figure out, because this is it's sometimes closer to me and sometimes farther away from me, just like in the Romer effect that we talked about on the first day of class, we can see that sort of modulation of the arrival time of those pulses, and then I can figure out the period of that system. Because of the rippling of space and time, this orbit between, and this is an artist's depiction, the orbit between these things is going to actually wind up decaying over time. And there's a very, very clean prediction if you have 2 point masses in a binary orbit around each other. If you know their masses and you know their orbit and the eccentricity, you can figure out how long it takes before these things wind up smashing together. In a Newtonian sense, if I have 2 point masses in an orbit, say Earth and Sun, or 2 suns orbiting each other, that just happens forever. Assuming the system doesn't lose mass, right, it just keeps on going around forever. But in GR, there's actually a gradual decay of the orbit because the whole orbit is leaking out energy in the form of gravitational waves. So think about it this way. You've got this rippling of these waves that are spreading out. And the measurement of this pulsar was a great confirmation of one of the predictions of general relativity. I'll turn off the lights. These black points are data points showing basically how the orbit was decaying in whatever units we have over here over the course of a number of years. And you see this black line going through these data points. It's unbelievable. Right? This is exactly what general relativity predicted of how the orbit would wind up decaying, and basically all the data are exactly consistent with that. So this was the first indirect evidence for the existence of gravitational waves. Yep.
Why does radiating gravitational waves decrease the energy of a mass? Because the gravitational waves are in space and time. But the mass
Sorry, it's not decreasing that. What it's doing is it's decreasing the energy associated with the entire binary. Right? So there's a 1/2 mv squared of both of these objects. Even if I'm not changing the mass of the objects, if I wind up removing energy from the system, that has to come from the orbital motion. Right? So this whole thing is just sort of getting weaker and weaker and weaker. And so the orbit winds up decaying.
also, in that case, shouldn't everything be getting gravitational waves from everything else in the universe too? So does that in general cancel out?
Oh, so that's a good question of where that energy actually goes. It's very hard to absorb that energy and make use of that energy. But indeed, there are gravitational waves all around us, just like Air Bear's Wi-Fi signals. It's easier to absorb that energy, the Wi-Fi signals. But no, gravity waves are passing through you because they basically only interact gravitationally, and you can't really capture those. In principle, you could set up a very, very precise system so that as a gravity wave passed by, you wind up sort of inducing real spatial motion, and that actually has an energy that you wind up pulling out. But it's actually really, really hard to do that. So for our purposes, think of this binary system as, in an isolated sense, energy is flowing out of this, but not in the form of light, in the form of gravity waves, right? Essentially, it's a completely different spectrum. And that's just sort of propagating out forever, right? It's just going out throughout the universe. Now, if there's an equal number of those binaries all over the place throughout the universe, then the sort of net divergence of gravitational wave energy in any one place is going to wind up being 0 on average. Yes?
So since these things are emitting light or energy, or whatever they're emitting, especially the pulsars, wouldn't they be decaying anyways if they're already emitting energy?
Yeah, but the rate, right, so that's a good point. If I just take the sun and I take the Earth and I let the sun just radiate, it's losing energy all the time, right? And if we want to stand far away and we want to think about gravity as a curvature, mass and energy are essentially the same, so the curvature over time is going to wind up decreasing. But it's a tiny fraction of this effect right here.
So this is like after you take that
I think you can't even see it in this, right? Because we could work at that, probably get that on your midterm. Yes?
So how exactly does the interaction of the curvature of these two objects produce gravity waves?
Well, because you have, so the orbits are being dictated when they're far away, more or less by just the Kepler's third law, right? When they're close in, this is assuming that they're circular. When they're close in, they're moving, and these actually turn out to be very, very similar masses. Basically, the center of mass of the system is more or less directly in between them, although there is an eccentricity to the system. They're actually, one of these takes a little step because it sees its local curvature induced by the other system, as the other system was, at sort of c divided by t, or sorry, d divided by c time away. Because there's this sort of whole sort of, in electrostatics, you call it a retarded potential, essentially a retarded curvature. And then you move a little bit more, and you are inducing a change of curvature as viewed by the other system. So there's this mutual change of curvature, and that's changing in time. And the way that that sort of manifests itself, think about sort of taking a pebble and dropping it in a lake. What's actually happening is the pebble is displacing water downward, and then the pebble keeps going. The water sort of recovers, and then it comes back down, and it's that oscillatory signal that winds up sort of propagating these ripples. And it's clear that those ripples and sort of the wavelength of those ripples has to be comparable to the instantaneous orbital period of the system, right? So you can imagine as the period winds up decaying, the wavelength winds up increasing. Turns out that if you win a Nobel Prize, you're very happy. Hulse and Taylor won this in 1993. Yes, before I move on.
So can we calculate expected wavelengths and frequencies?
Yeah, I'll get to that now. So this is sort of indirect, right? Because it's showing the effect of some source of energy leaking out. It turns out it looked exactly like what was predicted from general relativity. This is a really good indication that there are gravity waves in the universe, right? Doesn't explicitly tell us that gravity waves are moving at the speed of light. We don't know what the amplitude of that was. We just know that sort of the time average value turned out to be exactly right. But there's this hope that we can actually detect gravity waves very precisely. And that is basically by using the Michelson-Morley experiment. Remember, this is what they tried to do in the late 1800s to measure the existence of this luminiferous ether. And that was to measure slight changes of the speed of light in different directions as the Earth was moving through this ether. Here, what they're trying to do is send a laser light down this 4-kilometer vacuum tube and another laser beam down this other 4-kilometer vacuum tube, have this stuff come back, interfere, and try to figure out what the differential change of the length of that arm is relative to that arm. If I have a gravity wave which comes in this way, it actually winds up shrinking and increasing this length. And what the gravity wave is doing is it's changing this sort of overall local curvature of space and time. And so what it's actually doing, as manifest by us, is changing the total path length, this d script dl. It's changing that path length. So then light effectively would be taking a longer path on this arm. And then it sweeps by, and then it would make this one go, right? If the gravity wave source is over there. So there's been something like $1 billion of your tax money put into this. They haven't found anything, but they've reached the sensitivities they thought they needed to be able to see merging neutron stars out to something like 20 megaparsecs, so well beyond the local group of galaxies, and they didn't see any. Now, it turns out the rates of these things, because we can't see the Hulse-Taylor binary directly now, because the period is so long. It's 7.75 hours. We have to wait until sort of the last few milliseconds before these two things smash into each other to be able to see this. And the way we think about it is not that we're seeing it. Here's another depiction of that. Not that we're seeing it, but we're actually hearing it. This is what's called a chirp signal, and this is the last sort of moments before the two neutron stars smash into each other. And you see this period is going back and forth. What we're measuring here is what's called strain. It's basically the differential change of the length of one of these arms as a function of time until the merger. And as you get closer, the orbit winds up decaying very, very rapidly. and you wind up getting this whole thing sort of pushed together because this distance is related to the period of the system, and then you get this really big blip. And it turns out that the frequency of this for emerging neutron stars is in the audible range for your ears, so we can try to listen for this. It's sort of the last 3 seconds before a neutron star at 20 megaparsecs collides. That was it. Did you hear it? Let's try it again. Hello? There it comes. Oh wait, I gotta go back. Try it again. Turns out that black holes and black holes also merge with each other. We can listen for that. So it may be in the next several years that these detections will actually be made by these various systems. By the way, the black hole merger was a simulation of what would be heard by essentially the same thing I just showed you, where you had these two arms, but not on the ground, but in space. It's a project called LISA, and that'll cost many $billions of your taxpayer money. And it's probably not slated to fly now until about 2025. Yes? Yes, that's an interesting thing. So we know that the energy of light is basically just, or the luminosity, the effective luminosity, the flux that we see, goes down like 1 over r squared. What is that when we talk about the flux of a system? Well, think about this as in terms of waves. You usually think about power as the sort of square of the amplitude. What they measure is basically just the amplitude. So the amplitude goes down like 1 over distance, not 1 over distance squared. But yes, it has to be for just conservation of energy purposes. It has to go down with distance. Yes?
So that noise, is that what, like, LIGO?
LIGO.
LIGO?
Yeah.
Is that what that is going to make or something? What's going to make that noise?
Okay, so it's going to measure, if all things go well with advanced LIGO, which starts in about 2015, it's going to wind up seeing this sort of slight change of the lengths of these arms, right? And those slight changes is this thing called strain. And it's a differential change. So they don't know the exact distance, but they know that the distance between this arm and this arm changed by that amount. Okay, so this wave goes by, it's got this oscillatory effect, and essentially what they have are just glorified mirrors, and they're just doing an interferometer at the end of basically where they shut off the lasers. And they're making a fractional change in 1 part in 10 to the minus 21. So it's an incredibly small amount of distance change that they have to measure. So think of it as just sort of the distance change of an arm as a function of time. And it's an oscillatory signal, right? So it's going back and forth. And then eventually that oscillation happens very rapidly, and then it's just all gone. If you take that waveform that I showed you, what's called the chirp signal, and you just plug it into a phonograph, you would get what you just heard. It turns out the LIGO regime is sort of very similar to the ear's sort of audible frequencies. Now LISA is at a much higher frequency, much lower frequency. So they see much bigger objects over longer periods. Okay? Any questions about that? In some sense, this Hulse-Taylor Nobel Prize was really the 4th confirmation of general relativity, right? It was such a great prediction of general relativity, and it turned out to be exactly right. Let's go back to the Schwarzschild metric, and in particular, look at what happens when we wind up getting r approaching 2gm over c squared. Remember I said that delta t as measured by somebody in infinity is just delta tau 1 minus 2gm over rc squared to the minus 1/2 power. What is this person going to wind up measuring as I wind up getting r, big R, call it little r? getting close to this. This whole thing's going to 0, so it's going to wind up blowing up. So it goes to infinity. Nu r at infinity is just going to be equal to nu emitted 1 minus 2 gm over rc squared to the 1/2 power. What is this going to? Just going to 0. So something's happening. We have, in the first case, infinite time dilation. And in the second case, we have infinite redshift. As I'm sure you know by now, this R has a special name. It's sometimes scripted RS because it's called the Schwarzschild radius. Now it should be clear why that's the case. Something blows up with a metric. Right, we have infinities and we have zeros. This RS is sometimes called the horizon of a non-spinning black hole. It's kind of interesting, actually. We'll sort of flesh out some of the implications of this in just a little bit. But what's interesting about this is that you could come up with this number in a completely classical way. And so in 1783, there was some monk or something, a Reverend John Mitchell, who posited that you could have something called a dark star. And there, what he said was that you could have a star whose escape velocity was equal to the speed of light. So you think about a mass that's so compact that if you shot some, laser beam or light beam in 1783 from it, even light wouldn't be able to escape. It would have to essentially fall back in. So the escape velocity, 1/2 escape velocity squared times the mass of whatever the object is of interest is just equal to gm divided by r from where you're launching off your laser. So this means that v escape is just square root of 2gm over r. If we set this equal to c, then we get this r of this dark star is equal to 2gm over c squared. V escape, just to give you some context, from a red giant star is something like 10 kilometers a second. Red giant. V escape from the sun, something like 600 kilometers a second. V escape from a neutron star is something like 0.5 C. So in 1783, they sort of did this trick where they thought about the weak equivalence principle, and they just said, let's forget about the fact that something has mass. Let's try to shoot something off that actually has mass at speed c, and let's see what that massive body has to be, given the radius at which I launch it off, for that system basically not to ever allow anything to leave it. So this is a purely classical derivation of the radius of a black hole, but it's also wrong. But if you ever forget 2gm over c squared, you can just write down that the escape velocity, the kinetic energy at the start has to wind up equaling the gravitational potential. The derivation is wrong, the classical derivation. Because one, it assumes implicitly that photons have mass. or I guess a related statement is that objects that have some mass, like a bowling ball, could ever be accelerated to speed c, and you've shown that that's basically impossible. And the other is that it assumes that Newtonian gravity applies basically, but we know that this is it's actually a strong field near compact objects like neutron stars and black holes. The other important thing is that think about escape velocity, right? Think about the escape velocity from the surface of the Earth at something like 17 kilometers a second. If I threw this chalk up at 17 kilometers a second in the absence of frictional forces, etc., it would leave the Earth's gravitational pull, right? It would leave the atmosphere, and it would just keep on going, and it would basically get to infinity as it's approaching essentially zero velocity. That's the definition of escape velocity, if there are no other massive bodies in the universe. That means that if I'm standing, say, at a few kilometers above the Earth's surface, and I shoot something out with slightly less than the escape velocity, I might see that particle come up and then just reach me and go back down. So not have nearly, or not exactly enough escape velocity, right? And think about sort of getting infinitesimally closer and closer to the surface of the Earth and not having just enough velocity to go past you and escape to infinity. In this sort of dark star idea, you can imagine standing on the surface or this horizon of this dark star and shooting off a laser and having the laser sort of just go up but not make it all the way to infinity and come back down, right? The light just actually propagating up and going back down. That's actually wrong. That actually doesn't happen in this extreme curved space-time. If you're actually shooting light from within this radius, this magical radius Rs, even if you're just a fraction of a little bit inside of that RS and you shoot off a light beam, if you're just a fraction larger than this RS, you don't see that light. There's something about the curvature of space and time for a massive body that's not spinning, so that if you're at RS and you're basically epsilon farther away from that, you don't see anything coming from it. That's weird. It's a very different conception of how things move in this very strong gravity limit than what you get if you think about this in a classical sense. Okay, so just bear that in mind. Anything that basically has mass. I lose my notes. Anything with mass m that is contained within Rs is a black hole. Rs for the sun, 2g m over c squared, is about 3 kilometers. It's clear that Rs in general is just going to equal 3 kilometers times mass of whatever it is divided by mass of the sun. Have you all seen this way of sort of giving answers to equations where you put in sort of a scaling of interest? But that means if I now have something which is 1/10 the mass of the sun, instantly you know what its Schwarzschild radius is. Inside a Schwarzschild radius, no information is going to wind up escaping. Any massive body, even you, if I crushed you down to a small enough size, could form a black hole. And I showed you this picture before. It's worth showing it again, of this idea that very far away from this massive body, the curvature is essentially the same. So if the sun got crushed into a black hole, if I'm standing out here in the Earth's orbit, I wouldn't actually notice anything. Right? I just keep on going around, other than the fact that the sun disappeared. But the radius of this black hole is not obvious, and this should be quite obvious, is not actually something which is a physical thing that you could step on. It's sort of just a location relative to where this mass is, such that if you do anything inside of that, nothing comes out. Right? We think of black holes as sort of like cosmic Las Vegases, like what goes on inside, stays there. Las Vegas pays me to say that every time. And inside, as I'm sure you know, all the mass that went into making up this black hole is concentrated at a single point. There's an infinity there. So there's an infinite amount of density. We don't actually know if that's the case. And we think actually the breakdown of general relativity, when it starts sort of facing quantum mechanics, happens at this so-called singularity, where you otherwise would have had an infinite amount of density. So you have infinite curvature in space and time. Because we think that all the mass that's actually flowing into this singularity may actually have a finite extent to it. So it's not actually an infinite density. That remains to be seen. We don't really know what's going on inside. Let's see. There's lots of stuff to talk about with black holes. Oh, yeah. The color scheme's not good. So black holes, as I've already stated in different ways, are not this sort of cosmic vacuum cleaners. Hold on one sec. And of course, far away from black holes, in the Earth's orbit, we more or less can just assume Newtonian dynamics, right? Because we're in a very, very weak gravity limit with respect to the sun and our distance from the sun. And as I said before, if we replace the sun with a black hole, basically everything would remain unchanged. Yes, yeah. It's effectively the same thing, right? And the way one way to think about it, of course, is that you have mass falling into the black hole, and as it's falling in, you think about an escape velocity. The escape velocity can be turned around the other way. If I start off at very large distances with no kinetic energy, only gravitational potential relative to that black hole, I wind up falling in, and by the time I get there, I'm at speed c, right? And so inside the black hole, think of all the mass basically as just mc squared, right? It's moving at velocity c. There's something really strange about this that it's worth sort of looking at with these equations. And that's the following. If you have an object which is falling into a black hole, and it's emitting a light pulse to you every 1 second according to his or her clock, me being outside of that black hole will wind up seeing the time between pulses increase, right? As they fall into this black hole, and this is something we already basically saw with pulsars, you can see this with white dwarfs, it's not as dramatic, but as you fall in, that sort of last pulse, as the person is falling in, winds up basically taking an infinite amount of time to get to you. And likewise, if they're sending out sort of blue laser pulses each 1 second in their own frame, by the time they actually fall in, that wavelength of that light will be infinitely redshifted, so you basically won't be able to see it. So the ramification of this is, if I'm falling into a black hole, I actually wind up sort of just crossing the event horizon and nothing really happens. There's nothing really special, again, at the event horizon. In fact, you can show, this is something that we'll work on next week, you can show that the tidal forces on, say, you, so that is the differential stretching of your legs relative to your head, for a very massive black hole, sort of 10 to the 8 solar masses, is not enough to actually stretch you apart. In fact, the best black holes to go through are the biggest ones, because they have the least sort of differential tidal forces as you go through. Anyway, if you're falling through, you just fall through, and then you just head towards the singularity. End of story. If you're sending out light pulses to people, and sort of blogging, hey, I'm falling into a black hole, this is super cool, that information that you actually hit the event horizon never gets to them, or it gets to them at an infinite amount of time, so effectively never gets to them. That means that as somebody's falling through and somebody's watching them fall through, the best they could ever do is see them get epsilon close to the event horizon. So what you really see as an observer far away is that if a black hole was actually made up of lots of different pieces of mass as a function of time, because maybe it's accreting gas. We'll see more of this later on. You basically wind up seeing all the mass effectively accumulate right at the Schwarzschild radius, which is really strange, right? Okay. Any questions about that? So black holes are really weird. Yeah?
So, if we assume that the singularity is just a collection of dense mass, when two black holes come together, they combine. How come their gravitational forces don't cancel each other and the masses may be free?
Oh, so how come when you have black holes that are merging into each other, you don't sort of mess up their horizons?
Yeah.
And then you can see the singularity?
Sure. Yeah.
I don't know. It doesn't happen. I don't know. I don't know the answer. I mean, it's a reasonable idea, but people have done numerical calculations where you take two black holes and you merge them together, and so you have to deal with all this changing space-time and all this sort of fact that this information traveling at the speed of light, et cetera. And they wind up showing that you don't actually you never get a naked singularity. But I can't give you a deep reason why that actually would happen or not. So this weird thing of this kind of mass getting infinitesimally close but not actually falling through, as viewed by you as an outside observer, is pretty weird, right? And it's kind of easy, and because it's so exotic, to think about black holes as these incredibly exotic objects. But black holes are actually the simplest objects in nature. Because all of their properties are basically defined by three things. One, black holes have mass. Black holes can have spin. And black holes can have charge. Turns out that in nature it doesn't really make sense to think of something that actually has charge. Massive bodies don't have charge because if they're slightly positively charged, they just pull a few electrons from the neighboring environment and then they get themselves neutral. There's a strong tendency in nature for objects to become neutral. So the things that are important with spin or rotation, the thing that's important, of course, is understanding how the spin winds up changing some of the properties of the black hole. First, let's say that the horizon, so now not the Schwarzschild radius, is just going to be equal to g over c squared times the quantity m plus m squared minus a squared to the 1/2 power. A is what's called the dimensionless spin parameter. And A goes from 0 to 1. 0 when it's not spinning. So let's see if things work out. When it's not spinning, A equals 0. So we have an m here, so we have 2m. So 2gm over c squared. So we get that when A equals 0, our horizon is equal to the Schwarzschild radius. And A is going to be equal to the angular momentum, which we'll call J, divided by this maximal angular momentum. And there's a maximal spin of a black hole. Hold on one sec. And you can imagine why there might be a maximal spin of a black hole. The maximal spin is just going to wind up being such that at the surface or at the horizon, the speed at which something moving along with that horizon is going at the speed of light. If that speed was any faster, if it was rotating any faster, then you have weird sort of information paradoxes, right, where a particle would know where it was before it got there. Right? So c at basically the horizon is going to wind up being the fastest it can go. And this J max is just equal to g m squared over c. It has to be that unit in units, right? Because this is just going to be some sort of r times m times v. Vc, m, there's only one mass involved, so there's, and this r has to be related to gm over c squared. Anyway, so this value, it's evaluated in your book, so I'll just give it to you here, is 8.81 times 10 to the 41 kilograms meter squared per second. That's the maximal angular momentum of a black hole. Interestingly, if you just sort of do the numbers out for the sun, and you assume that the sun is sort of a rigid body and just a big ball of gas that's rotating at the speed that it is, for the sun, this number is, I wrote it down, 1.63 times 10 to the 41, same units. So this is like 18% of the maximal spin of a black hole. It's weird, but most stars are actually semi-close to their maximal spin rate. And neutron stars, in fact, you can put a limit on how fast a neutron star can pulsate given that consideration. So it's actually not unreasonable to think that in nature, black holes would actually have some amount of spin to them. What do we wind up seeing about this horizon distance when we actually have some spin? If I wind up increasing that spin by enough, then I wind up getting a slightly decrease from the Schwarzschild radius. So spinning black holes actually have a smaller horizon, which turns out to be very important when we start thinking about black holes in nature. It's something that we'll wind up doing. We'll wind up doing that at the beginning of next class. Yeah.
For a spinning black hole, if our horizon is smaller than your Schwarzschild radius, how will you physically interpret what the Schwarzschild radius is for a spinning black hole?
It doesn't make sense. It's not a Schwarzschild metric. It's what's called the Kerr metric. And then that complicated ds squared, which looks really complicated, gets much more complicated. You can still do all the same physics and all the math, but now that you have this spinning, it changes what actually happens with that metric. One of the things that changes, this is really weird, is that you have something called frame dragging. The spinning black hole, if you want to think about it, takes space-time with it and drags it around. So don't think about this sort of fixed metric that's got some curvature in it. Think about that fixed metric with curvature and then send it down a drain, and the whole thing is spinning around. If you put yourself near a black hole that's spinning, there are locations around that black hole, and this volume is called the ergosphere, inside of which you have to spin in the same direction as the black hole, right? Because the black hole is dragging your space-time coordinates with you. And if you want to go backwards, you better be going really fast in your local inertial reference frame. And inside the ergosphere, you'd have to go faster than the speed of light to go back the other direction. Or the way that your book talks about is inside the ergosphere, there are no stationary observers. They have to be moving with some amount of rotation around. Likewise, there are no observers which are moving against the spin of the black hole. Outside of the ergosphere, you wind up being able to, with enough energy or enough force, stay stationary with respect to this spinning black hole. There was a question. Yes?
Right at the edge of it, if you wanted to stay perfectly, can a photon stay perfectly still?
What's that?
A photon moving at the speed of light right at the edge of the ergosphere against the rotation, it would just be sitting still.
Yeah, there's infinitesimally not. There is no place where that is exactly the case, because you're either slightly inside or slightly out. But yes, there's that. That actually defines the mathematical point where that's the case. Good. But as an outside observer, there is no place where that photon could be allowed to stay still.
But for an outside observer, if it's right outside, wouldn't they still see it going at sea? Or
Yeah. They have to see it moving at sea. Yes?
How do you measure the speed of light?
Good. Okay, so this is interesting. Well, first of all, there are orbits that I can take as a particle that I go into the ergosphere, and I'm not sort of inexorably pulled in, because the ergosphere is actually larger than the horizon. So there are actually orbits that I can take where I can go in and then come back out. And the reason why it's called erg is because erg, or ergon, is the Greek word for work, and erg, as you know, is a unit of energy. You can actually gain energy by going through this ergosphere if you have the right trajectories. So particles which are moving through the ergosphere have the ability, they don't always do this, but they have the ability to actually, if they come out, have more energy than they came in with. And where do you think that energy comes from? It comes either from the mass of the black hole or the spin of the black hole. So in fact, you can imagine throwing something in, and you more or less zap some of the spin energy of the black hole, either the spin or the mass or both, right? The way in which we measure, and we'll see more of this when we actually, I'll show you some of these measurements. Hard to see this. The way in which we measure that a black hole is actually spinning is we wind up sort of looking at the overall effect of mass that's swirling around it, and we wind up seeing the gravitational redshift of that mass. And it turns out that around a spinning black hole, you wind up getting sort of extreme redshifting and blue shifting, depending upon how you're viewing that mass inflowing in. So we also get very strange deflections. We can even get sort of light which is kind of wrapping around the black hole. And what we'll wind up seeing is that there's some very solid predictions in the context of accretion disk. So accretion disk is basically mass flowing in to this black hole. The mass itself isn't flowing in on radial orbits. It's going to have some angular momentum associated with it. And that angular momentum winds up basically, there's some frictional forces. You wind up actually having orbits decay. So instead of moving in circular orbits, eventually things start spiraling in. We wind up having these accretion disks. And in a spinning black hole, it might be a little hard to see, the distance into which a particle can move before it's in what's called the last stable orbit, where it just basically has to plunge in no matter what to the black hole, is actually less. And as we'll see in accretion disks, in a simple accretion disk, there's a temperature dependence to the accretion disk. And the closer in you go, the hotter that material actually winds up being. And so one very obvious prediction, if I had a black hole of the same mass and one that's spinning, say, near maximal, is that the horizon is smaller, and therefore I can actually get material closer in, therefore it should actually be hotter. So for a given black hole mass, spinning black holes are actually hotter. That's one thing. And for a black hole that actually has some spin, you see actually a huge asymmetry in what's called the blue wing and the red wing due to the Doppler shifting of the material as it's emitting towards you in the accretion disk. And we'll see some examples of that. In fact, black hole spins have now been measured for a number of different black holes. Last thing I wanted to say before we ended is that there was this big controversy, and I've been sort of telling you the old way of thinking about black holes as these very simple bodies, of the fact that black holes are very simple, and that the only thing that matters is their mass. So basically the question is, if I made a black hole out of like an entire library of Shakespeare books, is it the same black hole as if I took all of you and threw you all in with the same mass? Sorry. And the answer used to be, yes, it's exactly the same black hole. This is called the no-hair theorem, the idea that black holes are truly simple and don't care about what mass is interior. And Stephen Hawking had this famous bet. I'll post the slide so you can read this all later. But essentially, he believed that all information was lost. So if I threw a volume of Shakespeare into a black hole, there was nothing about the black hole as I could view it that would tell me that it was made up of Shakespeare volumes. And this was some sort of contradiction, one that I don't quite understand, with quantum mechanics, that information can't be completely lost or destroyed. And there's sort of now this change of idea that indeed black holes have a bit of hair, that they actually have and retain a little bit of memory of what it was that made them up. So I guess we'll end with this, and We'll start up on Tuesday with a discussion about black holes in nature. And we'll start off with sort of the simplest way to infer that there's a black hole. That's just by looking at the dynamics of stars around a black hole. And then we'll get into accretion disks and accretion luminosity. And we'll end on Thursday with a discussion of quasars, or active galactic nuclei. And then you'll have your midterm the following Tuesday.